If anyone wants to go to the bathroom, I think we'll wait for like 5 minutes and then start. It's slated to start in like 5 minutes, so.
Well, yeah.
Yeah.
Yeah, I'll just send my message. Yeah, I was looking at it. So that was AlphaGo, not AlphaGo Zero.
Yeah.
Yeah, this one's
Yeah.
my understanding is Zero.
Yeah.
Zero starts from instead of learning based off other Go games, it just starts off with here are the rules figured out.
Yeah. The first slide.
Oh, I wasn't sure if the
Yeah, no, it was the documentary was made like
yeah.
while all that stuff was happening, and AlphaGo Zero came out late last year.
Was it the same team?
That did.
AlphaGo Zero?
Yeah. Actually, Ben Bray is the co-author of
Is he good?
Yeah. He's like towards the end. He's like 55. He's actually useful.
Really?
Yep.
You don't play rematch.
What?
You don't play rematch.
So they actually, yeah, in May 2017, they played the current best, well, like the top ranked player. I think Lee Sedol retired. So he had planned to retire in like early 2016 and he up, like kind of towards the end. He was planning at the time. So I think he was like, all right, I'll do this one last time. But then he lost, so he had to like come back and rename himself. But I think, yeah, about a year later, they used an improvement again. I'll okay, go through the timeline. Yeah.
Do you have any idea how many public games AlphaGo play?
Public?
Yeah. Like normally, like they would play a tournament, right? Is that how Go is played in tournament style?
Yeah.
So like a normal player will play hundreds of games.
So they only played like these kind of high profile ones, except for one period where they kind of secretly played them online against people, and no one knew who it was. They just knew this person was winning. Yeah, it'll be in this timeline as well. What?
You never know who's playing. It's not human. It's another machine.
Right, it was online, so yeah, it was just a screen name and moves being made.
I heard people were like hypothesizing that maybe it was like not AlphaGo, but just something that was doing it.
Like a new thing. Yeah, there's a lot of. It's funny. They were testing out like a new modification for the algorithm. That actually it's this. They're testing out a new version of Monte Carlo tree search, which is used in AlphaGo Zero, same version. So yeah, I think we'll get started. I think it's about time.
You just like randomly sample like a tree
I'll explain it.
or okay.
Okay, so this is Understanding AlphaGo Zero. I'm Jason Mancuso. This is at the Cleveland AI Group. This is online for those of you who are here. It's being live streamed to YouTube. For those of you online, we just watched the documentary that's on Netflix, and we'll be talking about how AlphaGo actually works. We'll be talking about AlphaGo Zero, and I'll explain the differences right now. So this is the timeline of kind of the major events of AlphaGo. These are all the different variants of AlphaGo that have appeared. AlphaGo Fan was the one that beat Fan Hui in the documentary. AlphaGo Li was the one that beat Lee Sedol in the documentary. AlphaGo Master was the one I was just talking about, that there's this mystery player that registered on the online tournaments called, it was just called, well, originally it was called Magister, and then it changed its name to Master like a day or two in. And then it was revealed to be this new version of AlphaGo. Then in May 2017, that same version, AlphaGo Master, beat CAIG, who was at the time the best Go player in the world. That was at the Future of Go Summit. And then DMind announced that AlphaGo would be retiring from human play. So it hasn't played a human since. And then, a few months later, October 2017, they published AlphaGo Zero, which learns completely from self-play without any human pre-training. Like Thol was describing in the documentary, how they first start out training it on like expert games. That is not the case in the newest versions. It learns completely from itself. They found that it performs better that way when you modify a few things. And then December 2017, they published a preprint on Alpha Zero, which they reported was able to outperform all previous humans and machines in all of Go, Shogi, and American chess, or not American chess, just Western, regular chess, according to us. So we're going to focus on these. I'm really going to focus on AlphaGo Zero because that's the latest peer-reviewed version of AlphaGo. Alpha Zero is it's essentially the same algorithm, just applied, retrained in 3 different times with the 3 different games, and it's literally like the same hyperparameters and everything. So yeah, we'll get started with the contents of this talk. We'll go through some background, talk about the architecture of the models underneath, then describe the high-level approach, how it learns by playing itself. We'll dive into the self-play algorithm, how that works, which is the Monte Carlo tree search. And then, there's also like one slide on results, but that points to other analyses of that, and then thoughts on the relevance, discussion, links, etc. So, background. Like it said in the documentary, most of these games, these 2-player games of perfect information, are analyzed using tree search, or they're analyzed using game trees, and the way computers can navigate through game trees is with tree search, which is, these algorithms have a long history in computer science before being applied to artificial intelligence. They just happen to work well in situations like these. So playing the game becomes searching through the game tree to find a sequence of winning moves. And because these are adversarial games, and each player's trying to win, and they're alternating moves. So that's why you can represent it as this tree. There's also a finite number of moves for each state, for each position, and everyone knows exactly what's going on. There's no hidden information. Like in poker, there's imperfect information. Everyone's got their own hand that only they can see, but they can't see everyone else's hand. Here, everyone knows exactly what's going on with the board, and everyone knows the rules of the game. There's nothing hidden. There's not even any chance involved. Like with backgammon, everyone knows what the game state looks like, but no one knows what's going to happen next based on, if I make this move, it could actually move here, depending on the roll of the dice. So that's why tree search is used in this case, because of all those different reasons. What I want to point out real quick is that this is kind of a familiar scenario. We have an agent, which is AlphaGo. We have an environment, which is the rules of the game, plus also the other version of AlphaGo, or here it was the human opponent. And then we have a reward. That's 0 at every time step, except at the end of the game. And if I lose, I get -1 reward. If I win, I get +1 reward. And that's going to be pretty fundamental in how AlphaGo learns. Anyways, to back up with tree search, brute force search is guaranteed to be optimal if you can evaluate these positions reliably and you have enough computing power. But for us, both of those are a problem with Go. There are a ton of possible moves, like they mentioned in the documentary, more possible game scenarios than atoms in the universe. And board evaluation is non-trivial. Again, that last game, everyone thought that AlphaGo was losing, but that's because we're actually not that great at evaluating these boards, and there's no quick way to do that. So this is kind of where AlphaGo, this is why that Go was such a problem, like a long-standing problem in artificial intelligence research, because of those two problems primarily. But we have this idea that's used in AlphaGo that we'll talk about. We're going to maybe, instead of searching through the whole tree, we need to find some way of limiting that search space. So if we have some idea of what moves are promising, which it seems like we do as humans, right? Like they said, it just seemed like a bad move or it seemed like a good move. We have that intuition. Maybe we can figure out a way to choose promising moves. If we can do that, then we can choose moves until we get to an unfamiliar position. Then we're going to simulate outcomes from that position. And then we're going to update our knowledge of the game tree using that simulation outcome. And this can all be done very quickly because we're using a computer, and because if that computer is playing itself, if AlphaGo is playing itself, it can do it much more quickly than it did in the game against Lisa et al. Then we're going to do this repeatedly until we're satisfied with our search or until we've hit some time limit. And in the game, like there are certain time constraints that usually happen in Go matches and chess matches. All these games usually have that time limit. But theoretically, you could do this forever. And the nice thing about this, it's called Monte Carlo tree search. It has asymptotic optimality, which means the more simulations we run, the closer we'll get to the result of a full game tree search from any particular position. So we don't have to search the whole game tree in order to get decent results. And we will eventually converge on the optimal result if we do this enough times. But the goal, again, is not to do this that many times. We want to do only promising areas of the game tree, because there's a lot of the game tree that we don't really care about. And another thing that's nice about this is that we can get creative with how we select promising moves. We can do so randomly, which is kind of how it's done in the literature before all of this, where you can choose moves that are most likely to lead to a win, given my current understanding of the game tree. That's called greedy search. Or you can combine 1 and 2 to balance exploration and exploitation. If you're there at our February meeting, I talked a little bit about exploration and exploitation and how that comes up in these kind of scenarios, where originally you want to explore because you're not completely certain with what you think is the right move, but once you've explored a little bit, you can be a little bit more confident about what you think is a good move, and then dive into that move and kind of exploit your knowledge of the game state. Another thing that comes up in AlphaGo are these neural networks. We're going to use convolutional neural networks here for a couple reasons. These are commonly used in computer vision, all of these image recognition algorithms, things that run autonomous vehicles. They're generally speaking convolutional neural networks. There's a few key differences with how they work versus like regular feed-forward neural networks. The main difference is that they take advantage of spatial relationships in the data much more efficiently. They do that by replacing the linear transformation between each layer with a convolution, which is kind of an old like geometric mathematical kind of operation that has a lot of literature behind it. But the motivation here is that Go is all about gaining territory. It's a very spatial move, and we're essentially interested in making choices based on spatial information. So this is kind of a natural fit for the problem of Go. Another thing that's nice is that Go is rotationally invariant. You can rotate a board and it's still the same game. So that's a nice property for these kind of neural networks. This is kind of more for completeness. I'm going to skip over this. It's kind of an advanced version of convolutional neural networks. That's not super important to get the basic idea, but these slides will be online, so if you're interested in that, you can check them out. I'll send a link to the group once we're done. So then we're going to dive into the actual architecture of the neural networks that, or the neural network that AlphaGo Zero uses. This is a little bit different than the original AlphaGo that was presented in the film, but it works much better. So this is the architecture. It's pretty long, as you can see. So we're going to focus on this large chunk from the bottom, which is where the data goes in, to the top where the result comes out. We're going to focus on the bottom first. First, we have this thing at the bottom that's the game state. It's the stack of positions, essentially. The top is the current position of Black's stones, so just 0 and 1. If there's a stone, a black stone there, there's a 1. If not, it's 0. And we do that for the previous 7 time periods as well as the current state. And then below that is a stack of the white positions. If there's a white stone there, it's a 1. And of course, the 7 time periods before the current state. And then the last one is either all 1s or all 0s, and it just tells the machine whose turn it is. If it's all 1s, it's Black's turn. If it's all 0s, it's White's turn. That's kind of the so that's actually not necessary, not completely necessary. And in theory, we should only need the current board state because each state is independent. And once you're at a certain node in the game tree, everything above it is kind of, it just doesn't matter to the rest of the game. Everything below it is what matters. But it turns out that, I guess, providing this much data, providing the past states of the game, help our optimization in practice. I'm guessing that's why they did it. It seems unnecessary, but it must have helped optimization, especially since they were balancing kind of the computational resources needed with performance issues. I think there must have been some potential trade-off between like the information gained and the amount of time and space complexity, like the amount of computing power that's required to optimize this thing. So they must have determined this as like a good way to represent the game. Unfortunately, the paper doesn't really go into too much detail about that, and I haven't seen anything online about why they do it. But and then, like I said, this is the convolutional layer and the residual layer. What this boils down to is we're going to use all this machinery to create a really rich, flexible representation of each game state. So we're going to build up this representation from the raw board position. And we're going to use that for a couple different things, which I'll talk about next. But so this representation is really what's going to be replacing human intuition. You know, Lee Sedol uses human intuition. A computer can't do that. So this representation is kind of its version of that. It's obviously not one-to-one. It's very different. Like we saw in the game, it operates very differently, or in the film. But in essence, that's what we're trying to replace. And all these other tricks that have been implemented in AlphaGo since the version that we saw in the film with AlphaGo Master and AlphaGo Zero, they're all going to support the optimization of this representation. What's different about this actually with the version that we saw in the film is that in the film there were 2 separate networks, but that's kind of wasteful, and it's better to learn a shared representation than that you can use for the policy and the value, which I'll get into now. So how are we going to use this? Well, we got to think back, and we got to remember this is an agent, an environment, and a reward. If you're here in February, like I said, and you attended the NIPS talk that I gave, it was in January. You may remember our brief introduction to Markov decision processes and reinforcement learning. But what this agent environment reward setup means is that Go is a Markov decision reward process. And the important thing about that is that we can use techniques from reinforcement learning in this situation. Reinforcement learning draws on concepts from behavior psychology to try to formalize like this concept of experiential learning that we do in a mathematical framework that we can then try to use with our computers. The idea is we want to learn to optimize long-term reward by taking actions in an environment based on the state we're in. And the key difference between this and kind of the AI that you see in industry is usually the AI in industry is all about predicting things. And it can do that very well. But here we want to do more than that. We also want to act. We want the machine to tell us how to act. When we're just predicting things, we have to ultimately decide how we use that information. Here we want the machine to use that information for us. So it kind of predicts as well as chooses. So when I say actions or policies, I mean moves in the board game. And when I say value, I mean the sum of the rewards, which here is just a 1 or a -1, marking a win or a loss at the end of the game. And then I'll also say, potentially, I don't know what I'll say, but I might say expected value, which is the average reward over all of the different games coming from this position that I'm in. So now that we have that terminology, let's get back to this representation. We're going to focus on the top right there. So this is the policy head on the right. It's how we'll choose the moves, like I said. At the top there, what's really important is just this in the top right, that 19 by 19 plus 1. That's 19 by 19 for all the different moves that a player can make, plus 1 for pass, because in Go there's a move where you can pass. You can just say, tell the other player to move. Usually you do that when you're confident that you're going to win. It's essentially saying, I don't really need to move anywhere. You can move, because it's pointless. So they do have that as a legal move, so they're represented in the policy. And then on the other side, we have the value. Ooh, wait a second. I missed something here. So at the top there, we have those 19 by 19 plus 1. We're actually not going to directly say, this is the move you should pick. We're going to give probabilities over all the possible moves. That's important for 2 reasons. First, it allows us to sample randomly, which means that we don't always have to choose the best move. We can sometimes pick a random move for the sake of exploration. And then it also allows us to act greedily, because it still gives us a measure of which move is most probable, or which loosely correlates with best move. We can choose which one to do as we want, which means we can explore early and exploit later, which is a common strategy for dealing with this. So back to the value. Value function is how we'll evaluate the odds of long-term success. Like they were saying, they represented it there as like a probability of winning. In AlphaGo Zero, it's actually a direct measure of the reward long-term. So it's some number between -1 and 1. -1 meaning complete certainty that I'm going to lose. +1 being complete certainty that I'm going to win. This is a measure of, it's kind of an approximation of the expected value, the average win or loss kind of value over a long period of games, a lot of games coming from this particular position. What this does is, if we think back, it provides a way to evaluate board positions, and that was one of the big things that we couldn't do when we were thinking about tree search originally. So another nice thing, the other part was that the state space is so huge, right? Well, because we're using a neural network, we can generalize our board evaluation and our action choices to new states that we haven't seen before. The whole reason neural networks are used in industries now is because they generalize extremely well in a very performant way. The same concept can apply here, even though the data is generated by self-play, which we'll get into next. This is the high-level approach. This is how AlphaGo is trained, not in particular how it plays games once you unleash it on a human. or another computer. So there are 3 stages. The first one is the self-play stage. It's essentially creating a training set for the neural network. It takes the best current player, which is itself a previous neural network that we either trained or randomly initialized, and then it plays 25,000 games against itself. We'll go into how it plays those games a little bit later on. At each move, the following information is stored. That's the game state, which we talked about, the search probabilities, which are the output of that policy head, and then the winner. If the game is won, +1. If the game is lost, it's -1. And it's going to store those at each move. Then, at the same time, we're retraining our network. We're constantly sampling positions from the past 500,000 games. And at start, I think they just randomly play out games just to fill this 500,000 so they can sample from it. And then you retrain the current neural network on these positions that you're sampling from the past 500,000 games. The game states are the input, and then the loss function compares the predictions with the actual results of the self-play games, which are stored, like we said, during the creation of that training set. So we're actually optimizing the neural network to build the representation that we talked about before. And we're optimizing over cross entropy for the policy, and then mean squared error for the value, which are common choices for both of those, classification versus regression. And a thing to point out here is that we're always retraining the current neural network. The self-play training set is generated by the best player that we've had so far. Here, we're always constantly retraining the current player. So even if the current player isn't the best player, the goal is that we plan on it being the best player eventually. So we're just going to train that. And then every so often, we're going to evaluate the network. It does this by playing 400 games between the current one and the previous best one. And whoever wins, if they win by a significant margin, here it's 55% of the games, then it's declared the new best player, and then it is then used in the self-play stage. So in practice, they actually do all of this in parallel, like that kind of. It's done in parallel asynchronously over time, so that it's playing itself, it's retraining itself, and then it's evaluating itself. Actually, the self-play stage, the only exception is the self-play stage halts for the evaluation to take place because it needs to know the result of that evaluation in order to know which network it's going to use to play against itself with. But yeah, so that's how this is done. When we're playing games against ourselves, we're going to use the Monte Carlo tree search, which we're going to go into now. And we do it in a little bit of a modified way with how it's done traditionally. So yes, this is how AlphaGo Zero chooses its next move. And choosing the next move is the essence of what it means to play the game. So first, we run the following simulation 1,600 times. The step 1 is to choose an action that maximizes this value, this Q plus U on the left-hand, top left. So the left-hand side of that, Q is the expected value. That's the output of the neural network on the left side that we saw. It's the value head. It's only there for pure exploitation. It's only measuring the probability of winning from a current state. The thing on the right is for exploration. It has to do with it's grounded in move likelihood. It's a function of the probabilities of a move and the times we visited that node in the game tree. And we're going to see why we used that in a second. So you continue to choose actions that maximize this value until you've reached a node that's a leaf node, which means it's a node that's unfamiliar territory, like I said before. Once we get there, we're going to pass that game state through the neural network. We're going to get our probabilities and our value. And we're going to use that to back up through the tree and improve our understanding of the tree. by backing up these edges, this n equals n plus 1. All that stuff is essentially just saying we're going to improve our understanding of the value of each state, and we're going to update the number of times we've hit that state in the tree. What we're going to find is that the number of times we visit, because we're choosing where to go with our neural network, the number of times we visit a node is actually going to correspond very well to our chances of winning. So we're going to want to explore those nodes more in the long run, and that's going to be our best way of choosing which action to do. The more we explore, the better the move is. The better the move is, the more likely it is we want to make that move, which I'll go into now. Yeah, we select a move based on those n values. We can either do it deterministically, so choose the node with the highest n from where I am currently. Like in this case, it would be, we would choose the node on the left because, or the action on the left, because it's been visited the most during that simulation. Or we can do this stochastically, so we can kind of weight each of those actions with the number of times it was visited, and then we can sample from that categorical distribution randomly. So at the bottom there, like on the left, we have a 50% probability of going to that best move, but then we also have probabilities of going to the other two, depending on if we're exploring or playing competitively. And yeah, so in exploratory play, usually they had like this way of determining when to do exploration and when to do exploitation. That had to do kind of with, it depends on if they're playing for real against a human or if they're playing against themselves to get better. So yeah, that's essentially how it works. That's it. Just to go back and reiterate, this whole Monte Carlo tree search takes place in the self-play side. That's how we generate these games. Those games are then used to retrain the neural network. And then we also use this Monte Carlo tree search stuff to evaluate the network. And that's how we choose which version of ourselves is better now that we've played ourselves 25,000 times. Or 400 times, actually. But yeah, so the results are kind of, I don't need to really beat a dead horse here. We saw the video. But this is AlphaGo Zero compared with AlphaGo Lee and AlphaGo Master, which were the two previous best Go programs. It beat AlphaGo Lee in 3 days of training, of playing itself. And then 21 days in, it beats AlphaGo Master, which was the one that beat the 60 players online. So those 60 games it played online, those were against the top ranked people in the world. And it won 60 games in a row against them. And then that same version played in May of 2017 and beat the reigning world champion 3 games to nothing. That was AlphaGo Master. This AlphaGo Zero, by playing against itself and disregarding, not using any human data, it was able to outperform even that version of itself after 21 days. And then it becomes like, the best Go player ever in the world. After 40 days, it's like at the top of this ELO rating score. And yeah, there's a lot more evaluation in the paper. There will be links to the paper at the end. So some thoughts on the relevance here. There's a lot of, so there's misunderstanding, I think, in 2 ways around this, on the significance. Some people think that now that we have AI that can beat the best at Go, then we're soon going to have AI that can beat everyone at everything very quickly, and that might be true eventually, again, but no one really knows. This is a very, like I said before, this is a very specific situation that we're in, where we can use a lot of really cool tricks to do really well, but that's usually not available in a lot of situations. I'll go into that. But so one thing I take from this is that amazing technological achievements will continue becoming more common, especially in AI. I think this might be a truism, but watching that documentary, I mean, they did this all 10, 15, 20 years. Some people predicted 50 years ahead of time. No one thought this was going to happen now, but it did, like Fan Hui said. So I think it is still a good point to make. The question, though, is obviously, can we apply AlphaGo to solve real-world problems? Like these three, kind of a random sample of a lot of problems. The answer here is hard. So they retired AlphaGo so that the team who made AlphaGo could take on problems that would actually help society. Right? That was the ultimate goal. That's why it kind of had a short live as a professional Go player, because Go ultimately they're throwing all this money into it. It's a beautiful game. It's a good thing to do, but for research purposes, but it's not going to solve serious problems that we have. So the question is, can we do that easily? The answer is no, not really, not directly, for all the reasons I provided before. This is a two-player game of perfect information, alternating. It's very predictable. We have access to a perfect simulator, which means we can very quickly gather lots and lots of data, which is not always the case. And there are a lot of other problems with applying AlphaGo to real-world stuff. AlphaGo in Context is a great article about that, and I have a link to it. But I guess the point was that reinforcement learning in general, if we can figure out reinforcement learning outside of these very specific cases, maybe then we can scale reinforcement learning up the way that we did with Go and solve a lot of these problems that we're actually interested in. And the question then becomes, I think it's a pretty strong bet that once we figure out reinforcement learning, we'll be able to get narrow AI that outperforms ourselves at a lot of tasks. But will we be able to get artificial general intelligence? That AI that thinks like a human, breathes like a human. That's a huge question that comes up a lot. The answer here again is probably not. So there's this paper that came out in like the 2000s. Marcus Hutter, he's a researcher in Australia. He wrote down artificial general intelligence. He developed the mathematics and proved that if we could solve this mathematical framework that he put out there, that we would have artificial general intelligence. The theory is called AIXI, AIXI. It uses a lot of pretty complicated math. It's a Bayesian reinforcement learning agent over a space of not neural Turing machines, just Turing machines. And it basically tries to figure out the best computer Turing machine to be in to solve the given problem at hand. And it does so in a reinforcement learning way, but there are a lot of problems with doing this in practice. It's been shown that it's not possible to do given a lot of computing power that we don't have already, and we likely won't have for a long time. And there's a lot of interesting stuff on that, but it might still be an ingredient, this reinforcement learning. Maybe not AIXI, but maybe in some other way. Andrej Karpathy gave a talk at a Y Combinator conference on what will lead to general artificial intelligence, and he brought up AIXI, he brought up supervised learning, unsupervised learning, and he brought up reinforcement learning in a couple different ways. His conclusion there was that artificial life is going to be the best way we get there, trying to grow life artificially in similar conditions that it arose on Earth. So it's an interesting talk. There's a lot of slides there, a lot of good material. Unfortunately, the audio isn't there, so you just have to kind of go through the slides and see his notes. But it still was one of the most interesting talks that I've seen or haven't seen. Another thing that I thought about when I was going through this was this is kind of early evidence of the personal impact of AI, its disruption and automation. You can see it in a very personal level, what it does to Fan Wei and then to Lee Sedol, and also CAIG later in May 2017. He had a similar response. They all start out with this emotional distress, and then and they handle it differently, honestly. Lee Sedol, after the end of the match, was still actually kind of disappointed, and he said he would never trade this one game for anything, but that sentiment he kind of reversed on that later on. But Fan Wei obviously is he's very positive about it. He learns from it. He kind of became its teacher. The point here is that alienation via automation is a looming issue that we should all be taking seriously. And there's also, like I said, there's this element of disbelief when this happens, and how people handle that is going to be all over the place, honestly, I think. But it's also, will regular people, I guess, not like, so these top performers, these people who dedicate their lives to this one thing and do it very well, they're the best in the world, and then they get beaten by a machine, obviously they're very shocked and unhappy at first. But is that a reaction that we can expect only from those experts, or is that something that will generalize to the entire public? Which I don't think there's a clear answer to. Oh, also, there was this recent conference at Carnegie Mellon. They had this whole session on agency and empowerment. This was like a very strong topic there. This was a great conference, a lot of interesting talks, and it's all online at these links. So yeah, recommend checking that out if you have the time. I think of Fan Hui as like this model for the human of the future. He gets beaten by this AGI, and this AI, sorry, AlphaGo, and he's extremely upset. You know, those first 5 games that he lost, he was just shocked. He was the first professional in the world to be beaten by a Go computer program, which is not something you want to be remembered for, but like he handles it very well. You know, he goes on a walk essentially and comes back, and he's like, all right, let's see how did you do this? And he ends up joining the team at DeepMind. He ends up playing AlphaGo over and over, kind of becoming its teacher, like showing where its flaws are by playing it over and over, and trying to like bring it closer to how humans play the game. And I think this is a possibility, given like this alienation that we might see. There's a way for us to coexist with this stuff. I take that as, you know, it's pretty interesting to me. Like I think it's almost a guarantee that narrow AI will outpace us in these very specific tasks, regardless of what you think about AGI and whether it's possible or when it'll come or whatever. I really got to ask, like, is this the future of labor in these, once this stuff arrives, once it makes its way into the market, once it's in all these industries, like, is this what's going to happen to us? It's an interesting thought. I figured I'd throw it out there. Oh yeah, and again, Andre Karpathy has a short story about this actually, called "The Cognitive Discontinuity." Like, what will AI look like in 100 years? What will we look like with that here? And he kind of comes to the same conclusion, where we become like these mechanical Turks, except we are training AIs to do these jobs. And yeah, it's an interesting story. I would check it out. It's pretty short too. Like it's not a bad read. For the reading, there's a lot on AlphaGo. DeepMind publishes a lot. They've published like 4 papers on this, I think. And there's a few other things. So the cheat sheet, number 4, that's what I used for a lot of these graphics. David Silver's keynote at NIPS was really good. That's on YouTube. This was Alpha Zero. He was presenting about Alpha Zero, which is the follow-up to AlphaGo Zero, kind of. Then someone wrote Alpha Zero for Connect 4, which is pretty funny. They just did it kind of like as an experiment. They used Python and Keras and played it out. And Connect 4 is obviously a much easier game, but it's cool to be able to see the code, because DeepMind, this is all proprietary Google code. They haven't released the code at all. So it's nice to have that as a kind of a reference, even if it isn't the real code. And then the AlphaGo website, they have a bunch of like blog posts for people who aren't interested in reading the actual research papers and aren't interested in all the language there. They have kind of the more lay person's audience, like articles that are devoted to that kind of, those kind of audiences. So yeah, that's pretty much it. If you guys want to talk about it, I'll be here. And I meant to say, like, if there are any questions on the material that I presented, I was hoping for like an interactive thing. I forgot to mention that. But if there are any questions, I'd be happy to answer them. And yes.
So reinforcement learning it's at least 30 years old.
Yeah.
And sometime in the early 90s, I used to go to a neural network conference